Hello.
Hello, everyone, and welcome to the CMS experiment.
Welcome.
My name is Claire Lee, and
My name is Andres Delannoy.
we will be your co-hosts for this virtual visit today, where you get to go inside the experimental cabin and see the actual detector.
Yeah, so it's an exciting time to be here, and we hope to show you guys as much as we can of the CMS detector. We have for this week no collisions, no beam, so we will get to go to the experimental cavern. And in addition to that, we also have the magnetic field of the CMS detector still on. So the magnet is on. So we'll also get to demonstrate how the strength of that magnetic field.
It's very cool. We have a solenoid magnet in our detector that goes to 3.8 Tesla. It's really strong, and you will be able to see some really cool effects of this. Just a bit of housekeeping. So if you guys have any questions, we would love to answer them. If you can write them in the Q&A panel, ideally in the Q&A panel, then we'll see them on our screen here and we can answer them for you. So especially if you want to know, like, what is that I'm looking at right now, definitely feel free to ask us questions.
Yep. So I think I'm going to start getting ready.
Okay.
And I think we can just head straight downstairs.
All right, excellent. Cool. So Andres is putting on his helmet and safety boots, and we'll be heading downstairs in our lift, almost 100 meters underground, where our detector is located. So let me move to the center here. So I'm going to give a little bit of an overview. I'm just going to keep talking while things are happening. So I'm just going to give a little bit of an overview about where we are, what this is all about, and why this is the absolute coolest job in the whole wide world, which is particle physics. So yeah, we are here in the CMS control room, and behind me you can see the CMS experiment crew, the ship crew, who are here making sure that our detector is running well, making sure that the people that are going underground, like Andres will, are all safe, and also when we're taking data, the ship crew makes sure that the data is good, the really the best quality data that we can have while the collisions happen. So yeah, what for some of you, let's talk a little bit about the LHC, the Large Hadron Collider. So the Large Hadron Collider, yeah, sure. Here's a nice overview picture of the Geneva region. So we are based in Geneva, Switzerland. You can see in the picture there's the Alps in the background, and then there's the lake. So that's Lac Léman, Lake Geneva over there. And this yellow ring that is drawn on the picture shows us where the LHC is situated on the map. Now, the LHC, the Large Hadron Collider, is actually 100 meters underground. And it's a tunnel. It's a 27-kilometer long tunnel all the way under the ground. And this is the tunnel in which we send protons. We accelerate them to 99.99991%, 9999991% of the speed of light, and we smash them together billions of times per second, just to see what happens. So Andres, what are you doing right now? Okay, maybe we can't hear. Oh, there he is. There he is. There he comes.
Yeah, sorry, we were just muted. So Noemi is now showing you the process of entering through the personnel access device, as we call it. And this device has several safety features, but I think the most, I would say the most remarkable is that it includes a biometric scan. So we will enter the underground areas with our personal dosimeter. And in this dosimeter, we have an RFID chip that identifies us and all of our access and safety trainings and so on. So the way that this works is we badge or we scan our dosimeter, and the system verifies that we have access. And then when we come in here, it actually takes a photograph of our retina, and it checks that with the database to make sure that the person holding the dosimeter is the correct person, right? If I lose this or somebody takes it, they still cannot get in here because they don't have my retina, right? So the iris, sorry.
Excellent. So yeah, safety is very, very important, and the safety system, we make sure that we have the most restrictions going in, but then in case of an emergency, there are no restrictions if you want to leave, because in case of an emergency, you want to evacuate as soon as possible. But we do make sure that we track every single person who goes underground into the caverns or the tunnels, just so that we can make sure that we know where everybody is at any given time. And this is the lift. So the lift is coming up from almost like 90 meters underground, where the bottom of the cavern is. So you will be going all the way down right to the bottom of that we have today. So that's very, very exciting. It's not often that we get a chance to take people into the cavern during the year. At the end of the year, there's a shutdown. There's a little bit of a shutdown period, and that's usually when we can go inside the cavern. But this is a special time, so you guys are very lucky to get a visit here now.
Okay, so we're about to get in the elevator, and Claire, I will let you take over because we will lose the connection momentarily, but we will see you downstairs.
Excellent. All right, can't wait. Okay, so yeah, let's go back to just chatting about what the LHC is all about. So the last I mentioned was that we were smashing these protons together billions of times per second, and that's all very well to do, but you actually want to figure out what happens when you smash these protons together. Now, protons are really, really interesting because protons are made up of small little particles called quarks. And these quarks are held together with what we call gluons. So when you smash two protons, it's actually the quarks and the gluons inside the protons that can fuse together and create interesting new particles, like a Higgs boson. The easiest way to make a Higgs boson is if you have a gluon from each proton, and those gluons combine, and for a very, very small fraction of a second, turn into a Higgs boson. So at these points where the collisions are happening, we build gigantic particle detectors. They have to be gigantic because the particles move so fast. But what they really are like big 3D digital cameras. So we have 4 points around the ring, yeah. And at each of these 4 points, we have a different detector. So Atlas and CMS are general purpose detectors. CMS is the one that we're at today. And then we have 2 more specialized type of particle detectors called Alice and LHCb. These detectors basically take a snapshot every 25 nanoseconds that the collisions are happening, so that we, the physicists, can then go and look at this data and understand what actually happened in that moment of collision. So maybe it created a Higgs boson, maybe it created a pair of jets. But I see Andres is downstairs, so let's go to him and see what he's up to.
Right, so just very quickly, I wanted to show you the process of accessing the detector areas in what we call, this is automatic mode, but it's very close to restricted mode. So in this case, we do a similar process. So I take my personal dosimeter and I badge. And as I mentioned before, this will check that I have access to the underground areas, to the areas that I'm trying to access. And in this particular case, this will call the control room where I get a key assigned to me. And this key is what we call an interlock key. So this means while I'm holding this, it means that the LHC cannot possibly inject beams into the LHC. This is part of the interlock system. So while I'm holding this, the LHC does not work. I have to return this key in order for the LHC to be able to physically operate. So with this key, I think I have to batch again. Maybe not. So let's try to unlock. Let's see. I think I might have to batch first again. I think there's a timeout. And then while it's blinking, I try again.
It's been a while since I've done this and entered with the key process, so you're actually reminding me. Oh, there we go. Things are happening.
Okay, so I will go through. And again, this will check my iris. There's some additional checks. So the system is designed such that I don't enter with any objects or with another person. If I bring in any material, it has to go through the material access device. So there are lasers that make sure that I only cross my legs twice and my torso once. So if you move around a lot or you're getting into the access device, you will not be allowed in. Let me see if this works again. All right, so we looks like we're more successful this time, and things are all right. And now it's Noemi's turn. In the meantime, I think you can continue, Claire. You can take over.
Sure. As you can see, we really make sure that people who really know what they're doing are the ones who go inside the cavern, especially when there is the risk of the LHC, being able to accelerate protons. So we make sure that while they carry these keys, then the humans are completely safe. Yeah, so just a reminder, if you write some questions in the Q&A panel or the chat, then we can answer them. If you have any questions, we'd love to answer them for you. Okay, so what else? Where was I? I was telling you about the CMS, about the detectors. Now, the way that these detectors are built is very clever. They're built in a number of different layers. And what happens is the layers are kind of centered around the place that the collisions happen. And as the particles fly outwards, they travel through some or all of the layers. And each layer measures something completely different about the particle. So when we put the information all together, we're able to see, we're able to figure out what type of particle it is. So the picture that you're seeing now is showing different types of particles traveling through all of these different layers. And we'll probably come back to that now, but this is the most exciting part here. So we're going to go back to Anders in the cavern.
I have just one comment on technical comment. They have to change the gimbal.
Oh,
that's why you see these weird shots.
Oh, we're wobbling.
Yeah. You will learn in a minute why we have to make it, but the thing is that they have to change to something much more rigid. I think Andres already has I see his smile, so
yeah. So we're almost all set. We just want to make sure we have a
we don't hear you.
Yeah, so can you hear me now?
Yeah, we hear you.
Yeah, okay, so we are just making sure we have a stable image for you guys. So Noemi, do you need yes? And we're gonna proceed and show you guys the detector. So one thing I can show you is we just went through the personal access device, and we have to now walk several meters, and you can hopefully see that there is a corridor, and then it turns right. So what you may not be able to perceive directly is that this is actually a very thick wall. This wall goes through the entire detector, and it separates what we call the experimental cavern, where the detector is, from the service cavern, where we have a lot of electronics. And Zoltan is now showing this wall, which we call pilier. And so this is part of the civil engineering of the underground areas, but it also allows us to work in the service cavern even while there are collisions happening at CMS. So we will go ahead. Claire, did you have a comment?
I was just going to say the ground here is actually really soft, so they have to. We're digging a big underground hole, and if any of you have ever been to the beach and tried to dig a big hole in beach sand, you know that things are going to collapse unless you reinforce them quite a lot. So that's what all of this concrete is for. It's to really keep our underground holes that we've dug, our underground caverns, nice and sturdy.
Okay, so we are now ready to enter the experimental area where the detector is. So I would just like to welcome you guys to the CMS detector.
Yay.
Yay.
So this is what CMS looks like in its business mode. And what I mean by that is CMS in this configuration is essentially ready to take data. We can, when we have a bit more time, let's say during the end of the year, we can actually open up the CMS detector. So I think Claire didn't have a chance to mention this yet, but CMS is, let's say, a modular detector. So that means that it's split up into about a dozen slices, or you can think of them as rings. And we are actually able to, in a very elaborate process that takes around 2 months or so, I would say, at a bare minimum, we can start to open up the detector, and there's many steps in the process, but the way we actually move these slices around is with this winch system. And you can see that it has these heavy cables that they actually come out of here. And these can be hooked up to the slices, and this are what allows us to move the slices. But before we're able to do that, we also need to use these orange air pads here. So what we do here is we have to apply compressed air through these air pads, and it's a little bit like a hovercraft, right? We have to blow compressed air, and this will lift up the very heavy slices. We're talking about on the order of 500 tons, lift the slices just enough so that we just reduce the friction enough to move them around. So since we're here, I'm holding in my hand just an ordinary chain. This is a metal chain, and it happens to be magnetic. And so what I'll do now is I will untangle it, which takes a bit of effort. And you can see that this chain just points straight at the detector. And this is just an ordinary chain. It just happens to be magnetic. But it gives you a sense of how strong the magnetic field is here where I'm sitting right now. Now,
this is just a few millitesla.
Yes, and in fact, this is just a fraction of the magnetic field power, if you will. In fact, inside of the magnet itself, which is deep into our detector, we generate 3.8 Tesla. And so this is orders of magnitude smaller, but it's still a very dramatic magnetic field. So something else I can show you, I mean, this thing is really pretty crazy. But I also wanted to show you guys that we have with us, we can leave it here for a second. So we have a little rubber duck, and this rubber duck has just a simple paper clip attached to it. And that means that the rubber ducky is attracted to this highly magnetized supports that we have here. What is interesting is that, again, it's a really, really quite significant magnetic field. So if I just let go, you can see that this rubber ducky just has a mind of its own, and it flies around everywhere.
Oops.
Yeah, so it's actually tricky to control exactly where it's going to end up. But you can see it's drawn to the edges, and this is where we have a strong magnetic field. So I don't want to spend a lot of time here. I just wanted to demonstrate the very strong magnetic field that we have. And we will walk around a bit more. Let me just show one more item that I have.
Yeah.
So I
just want to point something that even though this field looks significant, it is, of course, because this is more than 20 times more than that of the Earth magnetic field. This is very far from creating any biological effects. Okay, so this is completely harmless.
Unless you're a rubber duck with a paper clip stuck in you.
Actually, we have some trick. You see what Andras is doing.
Oh, yeah.
With these highly specialized magnetic indicators, as known as spanners. But obviously, they just very spectacular. They will not fly through the room if he accidentally drops them. So they will not create any short, unlike the paper clips. We don't play with paper clips there, because they might fly through the room and they can create shorts, and that would be the disaster. And on the other hand, it would not be so spectacular as the spanners.
Indeed.
So I think another point that is related to what Zoltan is saying is that when we build the detector and when we access the detector, we have to be very careful to use non-magnetic components and non-magnetic tools. So when you're building a detector, you have to make sure that all the screws are non-magnetic, and even if they are tightened very, very tightly, you don't want to take chances. So especially smaller components, we really have to be very careful to use non-magnetic components. So we will walk around a little bit, and you guys can take over. I think if you want to see something specific, you can let us know, but I think we will work our way upstairs to show you the view from above.
The reason why we have this magnet, by the way, is it helps us with identifying different types of particles. So the magnet will cause charged particles to bend as they travel through the detector, and positively charged particles will bend in one direction, negatively charged particles will bend in the opposite direction, and neutral particles will go straight. So that's a really helpful way that we're able to tell whether something is an electron or a positron, for example. So Andres was mentioning that the detector is built up in all these, it's built in all these slices. So he's walking down the length of the detector now. And this is actually underneath. You can see like the bottom of the detector. You can even
we can actually show you what a slice looks like. And you can tell because there's some gaps, and you can more or less see in between these gaps. If Noemi manages, you can see there's a little bit of light coming through from the other side. And you can see over here, we have a similar slice. And so we have many of these slices. Hopefully this gives you a sense of scale with me here standing in between it.
And the special thing about CMS was all of these slices were completely built up at the surface. And then each slice, I think there are 15 slices, each slice was lowered down a 100-meter deep shaft down into the cavern, but like completely formed. And yeah, the heaviest slice was about 2,000 tons. So
yeah, so we're showing here just since we're walking by, you can see the amount of cables and services that have to go into and out of the detector. And we mentioned there's a wall separating us from the service area or service cavern. So you can see that all these cables have to go down and under this wall. And so that's how and then they have to, some of them go up to all the way to the surface. But all of these they can be high voltage cables. So these red ones, that's most likely what they are. Mm-hmm. We also have low voltage cables. So it could be the white ones, it could be the blue ones. So often the green ones are fiber optic. So we also use a lot of fiber optic cables. Actually, these ones, I can tell you for sure, this is fiber optic. And yeah, green is for tracker. These are actually ordinary fiber optic cables, but these ones are bundles of, there's many fibers in here, and these are extremely long fiber optic cables. So you have to imagine that, again, some of these have to go all the way to the surface, and what we don't want to have is a lot of copper cables that go in a very, very long copper cables, which can pick up interference and they can act like an antenna. But again, you can see the amount of services that are required. And so these are just cables that we're showing you. But in addition to all this, there's what I call services can be also cooling fluids, for example. And this can take the form of water. So we use water to keep certain parts of our detector at a at a very specific temperature, but we also use cryogenic liquids actually. So we use cryogenics, and this could be liquid helium or liquid nitrogen that have to go into the detector. There is a reservoir at the top. We might be able to show you from a distance. And there can be other types of gases, for example, that we use for the muon systems. So there's a lot of stuff that we're not even showing right now. We might try to point it out in a bit.
Andres, we have a question regarding the electricity. So where does the electricity that CERN uses come from? And is any of that renewable?
So my understanding is that a very significant fraction, I think most, but I don't know what percentage, of the electricity used at CERN comes from the French
In principle,
grid. It's all, okay. So all of the power use or the energy used at CERN comes from the French grid, which, if I recall correctly, is 70-something% nuclear. So this is not exactly renewable, but this is a not a carbon-based. We're not burning carbon fuels in order to produce this energy. Zoltan might be able to, or maybe Claire, you know more about this. That's kind of all I know about it.
So what I know that the overall CERN energy consumption, electric energy consumption, is somewhere around 200 megawatts.
Yeah, that's while the LHC and the experiments are running.
Experiments, LHC, administrative buildings, my computer, my desk lamp, everything. So that's actually that's quite surprisingly low. This is something like a town with 200,000 inhabitants. So it's not too much. We have a direct connection to the French network. Also, we have a backup connection to the Swiss one, but we use rather the French one. And we are one of the three consumers of the French network who gets the 400 kilovolt network within the fences. Another one is Disneyland, by the way.
You can see the size of our detector, just that you saw the size with Andres over there.
Yeah, this is the point where we used to lose the guides when they get the magnetic field.
So this is an interesting point that Zoltan makes. So in previous virtual visits, we had a different phone, and the camera was really struggling to focus on the image because these what controls the focus are tiny motors, and they're susceptible to magnetic fields. So I don't know what kind of magic this phone has that is not susceptible to it, but that's how strong the magnetic field here is that you try to use the phone and it has trouble finding the focus. And since Claire mentioned this, I will just point out that I'm not very tall, but this detector, even though we call it a compact muon solenoid, is much larger, even in human scales. This is really a massive detector.
A four-story building.
It's a four-story building, and in the detector itself is 15 meters tall. But if you count the floors, right, you may be able to tell that there are 4-story, and we'll actually proceed to go up some of the stairs. We'll see what areas we can access and what we can show you.
There's another question about how much water CERN uses. Now, I don't know the number, but an interesting fact about the water use is, as Andres mentioned, we use the water for cooling. And there is a program right now to take the water that is being used for cooling, which is obviously now coming out pretty warm, and then circulate that in a neighboring village and use it for heating. So we're really recycling the water and helping provide heating for the surrounding neighbors.
So Claire, that's an excellent point, and this is actually going to the village that I live in. But I learned recently that this program, I believe it's aimed at schools specifically. So it's really benefiting the education system, if you will. Excellent. So I wanted to point out very quickly that if you were able to come to CMS and be lucky enough to be here during a time that we can bring visitors downstairs, this is the area where you would be taken to. This is the visitors platform. And so this would be your view if you come here in person. It's, of course, very spectacular to come see this in person. But I did want to point out, however, that you are getting to see from this virtual visit many parts of the detector that would be totally inaccessible to a normal visitor. So consider this a VIP visit, if you will.
Very
Maybe
much.
since we're here, I also can point out something interesting. So this is, of course, a very international collaboration. And if you look around different parts of the detector, you might see, for example, here, a flag. Maybe we can try to zoom in. But I will leave it as, maybe it's better if anybody recognizes the flag. I think it says it on it, so it's not a very difficult quiz. But the reason that flag is here is because this particular component of our detector was fabricated by Pakistan. And Pakistan is one of the countries that collaborates on this particular system that we call the resistive plate chambers. This is the end cap plate that is part of the muon system. And I think there's a few more. Yeah, I can show here, for example, we have some, I believe, low voltage modules. And if you look closely, you might be able to see that these are labeled UCLA. Some of you might be familiar with this university. It's the University of California, Los Angeles. And so many of the components and the systems, the modules, these are designed and built and commissioned and operated by different institutes or universities. And so that's something you see that's pretty interesting. If you walk around the detector and also in the service cavern, you will see stickers and you will see labels for universities and institutes around the world.
And this is quite an important thing, that we advertise our institutes, universities on the objects that we deliver here.
Yeah, so the collaboration is huge. I mean, it takes almost 5,000 people to build and operate something like this. So we have hundreds of universities and labs from around the world, everywhere from the US West Coast all the way to New Zealand. We have people working at different places, and the parts of the detector were built from all different places around the world, brought to CERN, built here at 0.5, and then lowered down into the cavern. And yeah, this is, so Andres is walking down the side of the detector right now, and we can see in, this is like in between like one of the slices there, but you can see it's very squished together. So yeah, this is as far as we can go, you know, without squishing poor Andres to death. We don't want to do that. So yeah. So we're not going to be able to go right to the inside of the detector. However, at the end of June next year, we're going to be shutting down the LHC for a period of 4 years or so to upgrade a lot of the LHC, but also to upgrade a lot of our detector. And part of that is actually going to be opening up the entire thing and removing the entire inside part of our detector, because it's going to get a brand new one for the next running period. So that'll be quite fun.
Yeah, we got a question about it.
Well, can I very quickly just show? So what we're trying to show here right now, Noemi is getting pretty close, but this is one of the muon modules, and this is you can maybe even see that it says super layer. So this is one of the drift tubes from the muon system. And this is certainly something you would not be able to appreciate without being exactly where we are right now. So when we open up the detector, you can see more of it, but even in the barrel areas, these are details that are not accessible normally. So yeah, we're able to show you. But yeah, back to you, Zoltan, for the question.
Oh, I mean, I was just going to say as well, like, you know, the detector is right here in front of us. You know, Andres can touch a lot of it. But there are also parts of this detector that once they were installed, they're just impossible to get to. So, like parts of the inner tracker system, for example, once they were installed, they might as well be in outer space, because you can't access them, you can't go and fix things. So yeah, it requires quite a lot of planning and thinking ahead when you design a system like this. You really have to be able to make sure that the parts that you're using are going to be able to survive for 10, 15 years or however long.
So maybe I can, since we're here, I can show a recent addition to our detector. So this orange block that you see here, this is what we call the new forward shielding. And it's an additional shielding on top of the original shielding, which is already very sturdy. And this is installed in place already in anticipation of the upgrade that Claire was talking about. And this, well, it also makes the process of opening up the detector a bit more elaborate now. But you can hopefully get a sense, this is not really an active part of our detector. I don't think we have much in here. Maybe the beam halo monitors maybe are in there somewhere. Maybe some Ratmans somewhere, but this is already sort of outside of the detector. And since we can see this reasonably up close, you can see these yellow supports. On top of the yellow supports, we have the hadronic forward detector. And the hadronic forward detector is part of one of our hadronic calorimeter. I think we haven't really been able to talk about the specific detectors, but I've already mentioned the mu1 systems, and we will talk about calorimeters as well. Since maybe I can point out really quickly. So here you can see that there's something that looks like a ladder. This is actually a lot of cables that go from the floor up to the hadronic forward. And so we need these because in order to open up CMS, we have to gradually lower the hadronic forward system without disconnecting the cable. So we call this a cable chain. This is it keeps the cable in place, but it is flexible, so it acts a bit like a chain. And when we lower HF, the hadronic forward, gradually, we can then slide it again. The supports and the new forward shielding have to be removed first, but you can imagine that if this blue support is not there, the scaffolding, then we can slide the hadronic forward into its garage. Maybe you see the yellow doors are slightly open, and there's a garage in there for hadronic forward. And only then can we start moving the slices, moving the mu1 wheels towards us in order to access the inner parts of our detector.
But just that shielding, that orange stuff, that's really there to protect our detector, our very sensitive detector components from the radiation produced by the LHCb, right?
What I heard about it is there are two different reasons why it was made. As a physicist, I would say this. Well, I don't need to be completely in, but anyway. So there are two different reasons for this kind of shield. One is that as a physicist, we don't like the beam-induced particles to be seen in the external detectors. We see them as a noise. Obviously, we want to reduce the noise. But as I heard just recently, the indication for the design of this equipment was completely different. The reason was that due to these stray particles, our equipments, especially the iron, might get radioactive. In this iron that we are using in our experiment, we've chosen the iron such a way that it should contain much less cobalt than an ordinary steel. Therefore, the cobalt 60 radiation will not be too much. Obviously, that it will be there, but this is reduced. However, the manganese, the manganese is one of the most important component of the steel factory, the steel manufacturing. Therefore, that should be there, and the manganese 54 would make a significant part of the radiation. Obviously, let me just make the remark: we are not a radioactive, not a nuclear blast, and not a nuclear power plant, but also we are talking about radiation, something that we can measure. Without this shield, when we increase the intensity of the beam after the next long shutdown, we would need to wait months longer before we could open the detector.
So it's all about keeping things safe, both keeping the detector itself safe, but also keeping the people who work.
It's rather to speed up the work.
Right. Yeah.
So you would not get a lethal radioactive dose even in that case if it would be there, but we should obey the legal rules as well, and the legal rules are very strict.
Andre,
So I wanted to jump in and show you guys where we are. So what you can see in front of us is a helium reservoir, and you can hopefully appreciate how large this reservoir is. I think Zoltan would know it's a couple of 100 liters.
5 cubic meters.
Couple of thousand liters of liquid helium. And this is part of the cryogenic system for our magnet. But I also wanted to show you guys a view of what it looks like on top of our detector. And you can see there's still a lot of infrastructure, a lot of cables, a lot of services. And we can also look up and show you, first of all, maybe we can go back a little bit and show you the main shaft of the CMS. Yeah, we can try to.
Can you get on top there?
Yeah,
yes,
we can get on top.
The only thing is that these barriers, the opening of these barriers are also magnetic, and they have to fight against a little bit. Noemi just told me, we had another visit in the morning, and Noemi just told me that they should be very, very careful not to pinch by the.
Yeah, so we are just going up right on top of the detector right now. And
you are lucky we are not operating the portal cranes today.
Yeah. So from here you can see the roof of the cavern, and the first thing you might, or maybe not the first thing, but you see at the end there's this yellow object. So that's a crane, and we do use the crane reasonably often. There's many heavy objects that we have to move around, especially when we open up the detector at the end of the year, for example, if and when we open up. And also you can see these red boxes, these funny red boxes all around us. So that's I think the last part of a very elaborate fire detection and fire suppression system. So in CMS, there's many specific dangers. There's cryogenics can pose a problem if there's a leak of cryogenic gas, then that can displace the oxygen. And so that's one example, but there's of course lots of electronics that pose a risk of fire in certain situations. So we have many layers of fire suppression and mitigation. And one of them, which I believe is last resort, are these red boxes that basically they're basically giant fire extinguishers. They produce a specific type of foam that will suppress the fire very quickly, and it's designed to fill up this cavern in minutes. I don't remember exactly how long, but just in the order of minutes. And so the last thing, since we're here, we can turn around, and we actually the handle for the camera got stuck to the metal. So I'm trying to shine some light up, but I don't know how clear this is. I don't know if you can see the top of the main shaft. So
that's not a black hole.
It's not a black hole.
So in fact, we don't see. So this shaft right now, it's covered at the top. So there's a very large slab and very thick concrete that covers this main shaft right now. But one of the things I wanted to point out is the shaft is very, very close to 15 meters in diameter, which again, this is the diameter of our detector. So this shaft, again, it's the cavern is 97 meters deep. So digging this shaft was a very expensive civil engineering project. And so we couldn't afford to build it much larger than the size of the detector itself. And this of course, complicated the process of craning down each of the detectors. I mentioned before the most lightweight slice, I think without counting HF, I think HF might be a bit more lightweight, but a muon slice will be on the order of, I think, 300 tons. If we take the heaviest slice, we're talking about the center slice that contains the magnet is built into the slice. So bringing down the magnet with that slice, that's on the order of 2,000 tons. And it was quite a challenge to bring down each of these slices safely, and exactly how to attach the safety ropes to them in a way that they wouldn't shift around with the center of gravity and so on. So a very complicated process, something we try to only do once in the lifetime of the detector. We don't expect to be bringing up the slices anytime soon, but there are upgrades coming, as Claire said, and one of these upgrades is very, very heavy, and it will replace the end cap calorimeters. I don't recall I don't know if this is confirmed, but I thought we were going to use the elevator shaft to extract the current end cap calorimeters. I don't know if they're also going to use the elevator.
The negative through this shaft, or the positive end through the elevator shaft, but both end cap calorimeters, both the one that we are removing and the new ones, each weighs something like 1,000 tons.
Yeah, and the tracker will go up through this one as well.
And of course, the tracker is going to be replaced. And I don't know. Yeah, even the tracker, not just the pixel.
Yeah,
exactly.
Yeah.
And we are going to remove the electromagnetic calorimeter. We will lift them up to the surface, all the 36 super modules, and we are going to replace the electronics on them. So this will be really a huge, large, major upgrade, refurbishment of the detector.
I mean, yeah, these are like one of a kind pieces. So you can imagine that, thousands of hours worth of work went into just building one of these slices. So when they were being lowered down, back in the early 2000s, there were a lot of physicists very, very much holding their breath, pretty nervous while they were lowering each one of these things. But so a lot of fun. There's some more questions.
Yes,
so
exactly. I would recommend to turn on.
There's a really nice question about the data use, which we can talk about for a little bit. But before we go to that, I just want to answer this other question about the inaccessible pieces. So as we mentioned, there are parts of this detector that you can't get to, and if modules or pieces of this detector die, we literally can't replace them, right?
Depends.
Well, depend, like the inaccessible ones.
Exactly.
The inaccessible ones. Some of them, even if they are accessible, we wouldn't be able to replace because we just may not have spares, or we just can't produce these modules anymore because they were built in the early 2000s. So it's been, a long, long time since some of these things were built. But we have teams of people. I, for example, work on the tracker, which is, one of these ones right in the center. And so we have teams of people working really hard to try to do everything possible to keep these things as alive as we can. And also a lot of the foresight in the design work went into making sure that we have things that can survive for 15 years of running.
Just think of the deep space probes.
Exactly. It's like if you whatever you can do to the Voyager, you can probably do to this, but you can't necessarily go and actually change something.
Exactly. But the way how we approach this work is very similar, as you said.
Yeah.
So we have to design the equipment such a way that if we cannot access, we should be able to do something to them.
Exactly.
Before we declare them completely dead. But actually, when I told Claire that it depends on the accessibility, or the urgent accessibility depends on the fault, the problem itself.
Yeah, for sure.
So if it is just one detector part out of the 120 million channels that dies, it's not so important. If it is a water leak inside the detector and we get liters of water spraying out, then the situation is different. it already happened to us. Fortunately, right before the year-end technical stop, so we didn't lose too much data. But this is also something that we are prepared for, and we know how to handle it. Obviously,
one of the things, sorry, like you can see in our control room, part of the huge number of monitors and things is because there's so much.
Exactly,
so many
we would
different things
immediately
to
realize.
keep track of, yeah.
And since the cooling that we have is also partitioned, we can lock out that partition, turn off that part of the detector. So you don't need to regard it as a Niagara Falls. That also takes us back to one of the questions, that how much water does it use? It uses quite a large amount of water. I cannot tell you how many cubic meters, but since we are using the water in a closed circle, it has no impact on the environment. That's very important. Actually,
So,
everything that, yeah, go ahead.
No, sorry to interrupt, but I believe I read some in the CMS website somewhere that just for the ECAL, which is the main water circulation or water cooling system, the flow of water is a fraction, I think a third is what I recall, of the jet d'eau, which of course, I don't know how much that flow is, but if you ever seen photos of you've been to Geneva, it's a very significant flow of water.
Yeah, if you sum up the 1 or 2 liters per minute that we have in the immune system in the jams, but if you sum up the hundreds or thousands of water circuits, then you get to an enormous number. But what is important, that's in a closed circuit. We reuse the water, we do not emit it in the nature. However, if we are at the emission, I'm pretty sure people are very curious on this. Of course, we emit the air from the cavern, we circulate out it in the surface. The gas system is not completely tight. We have a bit of a gas leak. We always control what we emit in the nature. Obviously, it is not just our.
Yeah, sorry, Sultan, just 2 quick things. So first of all, we might start heading up to the surface. Please let us know if there's anything specific that you want us to show. And since I have you guys for a second, we're showing right now one of the cable chains. And I mentioned before, when we open up the detector, we cannot afford to disconnect the many thousands of cables. We don't want to disturb them. So this cable chain here, maybe you can hopefully appreciate the linkages that allow us to sort of unfold the cables without having to disconnect them. So you can imagine that this moves to the right along this this channel or rails here.
And the cables there, these red ones are mine.
Yeah, gems. So these are high voltage. I guess they're gems.
Yeah, exactly. That's gems.
So yes, Claire and Sultan, let us know if there's anything else you want to see.
Sure, folks, last chance. If there's anything in particular you want to see about the detector itself, write it in the chat. You've got maybe like 1 or 2 minutes to ask. Otherwise, they will be heading upstairs. In the meantime, let's talk a little bit about data, data flow. So there's a great question here. What is the total data storage capacity of CERN's data center? And is it capable of storing all the data produced by the experiments? So what is the amount?
So LHC real data expected in 2026.
Let's go with like 1,000 petabytes per year, something like that. Is that enough? And remember, that is all of the experiments, not only the LHC experiments, but every experiment. There's a lot more experiments as well. Is that enough to store all the data produced by the experiments? Absolutely not. No, not even close. In fact, even before the data gets to the data center, we just don't have the capability of sending that data through from the detector to our first processing farm. So we have something that is called the trigger. You imagine that these protons are colliding every 25 nanoseconds. every 25 nanoseconds, our system has to make a decision. Does this look like an interesting event that we want to keep or not? And you can imagine, like, imagine if you are standing in front of a waterfall and you have a cup, like a small little drinking cup, kind of even smaller than like a small little drinking cup, and you can grab a cup of water every, like at a time out of this deluge from a waterfall. That is how much data is being produced by the collisions and how much data we can actually take and process ourselves. So there are a lot of events, most of the events, that we'll never know what happened in them because we just couldn't store we couldn't store the data from them. So we have to be very, very careful about what we select, because we don't want to be throwing away Higgs bosons or possible signatures of dark matter or something like this. So, you know, we have to take what theory will predict, and we have to take what we know happens, and we have to really, really optimize for our data flow to really make sure that we get the best.
That's what we call Monte Carlo on the picture that we are just sharing.
Yeah.
So actually, just by the numbers, sorry for interrupting
no,
you.
That's great.
As you might see on this picture, in 2018, the recorded data was something like 160 petabyte, which is a huge number. After this selection that Claire mentioned, without this selection, what we expected is 40 million petabyte.
Yeah.
Okay, so that's
from 40 million down to 160.
Exactly what I used to say, that if we would have needed to store 40 million petabytes per year, the storage element of God would not be enough.
Indeed. Andres, you were saying something?
No, I think he is just admiring the magnetic field.
We're just showing off the magnetic field.
Yeah. Okay, let me just
yay, more magnetic field.
Large.
Yeah, so I mean, if you're
this is usually when we used to lose people. That's the most dangerous thing. I mean, not that they get any harm, but they completely stopped working.
Also, we have to wear safety boots, safety shoes down there. And if you have metallic safety shoes, you will already kind of feel like you're walking pretty sticky.
Yeah, the modern shoes do not stick. But,
yeah,
but the boss had an old one, and he just stuck on the metallic surface he mentioned.
Yeah.
Okay, so I think we will start heading back up. Yeah, you can see even these really heavy objects, they point straight at the direction of the magnetic field.
Yeah, but be very careful. This is heavy, so it hit hard.
Don't get your finger trapped under there. All right, yeah, we'll see you up here in the control room now. So while they're going up in the elevator, I agree, it really does look amazing. So let's go back to talking about the LHC. There's a question here about how frequently the acceleration happens. So if we're talking about when the LHC is in its phase that runs at for like most of the year where it's colliding protons, if things are running smoothly, what happens is the LHC will fill itself up with lots and lots and lots of bunches of protons. And then it will accelerate those protons up to the almost the speed of light that they're traveling at. And then once they are at the speed, then the LHC team will start focusing the beams and everything and getting them ready for collision. That process to accelerate them from the energy that they came in the LHC at up until the 6.8 TeV, that takes about 30 minutes to accelerate them like that. Okay. Then we start colliding, and we typically keep colliding the beam for 12 to 15 hours. So we will have at least half of the day where the collisions are happening. And after about 12 to 15 hours, we've used up a good number of the protons that are in there. Nowhere close to all, but we've used up quite a lot of them. And it just becomes more efficient to empty the LHC and then refill with more protons. So what will happen after about, say, 15 hours is they will dump the beam, so get rid of all of those protons. The magnets will need to ramp down again, so not at the high 6.8 TeV energy where we have the collisions, but all the way down to the end. And that process also takes about another like 20-25 minutes to go down. And then they start the process of refilling, reaccelerating. So it's about 15 hours of collisions and then a 2-hour downtime where they ramp down, refill, ramp up again, and then start colliding. So I think that maybe answers the frequency. So what kind of work does the team do when we're not accelerating and detecting? Well, basically here in the control room, like I said, it's only a 2-hour period, but in that period, there's a lot of preparation work that needs to happen to get the system ready for the next 12 hours of data taking. Also, some of the detectors have calibrations and things that need to be run in these 2-hour periods. So there are on-call experts, and they'll get called. It doesn't matter what time of the day. It could be 3 o'clock in the morning, to do some special tweaks on their system to get the modules ready again for the next 12 hours of data taking. And yeah, so that's, while this happens, this happens for like 6-8 months of the year, like that. And then, the rest, the times when people when the LHC is not running, we've got a lot of maintenance work to do on our systems. Again, more calibrations, maybe a bit more like long, sophisticated ones that you can't just do in 2 hours, but maybe take a day or two. If there are any power supplies, powering modules that have died, the power supplies, are situated on the outside of the detector, so we can go in and replace those. And then, of course, during the long shutdown periods, like what we're going to have from June or July next year till about 2029, 2030, there's still, we've got so much data that we can analyze. So there's always physics analysis to do, people sifting through the data, trying to find interesting, things, maybe find a new signature of dark matter or something like that. So there's always a ton of work to be done on here. How is there internet down there? Well, you do realize that CERN invented the World Wide Web. So I would be very ashamed if we couldn't run. We can run, if we can collide protons down there, we can definitely get internet down there.
Wi-Fi 5 only yet.
There's obviously the important stuff is on fiber optic and cabled, but then there's also for the people there's Wi-Fi.
Yeah, so actually that was the biggest limitation of the image quality today. Yeah. I'm afraid that's Wi-Fi 5 they used. We also have mobile phone network down there.
Mm-hmm. Very important.
A very important thing. Obviously, that's also limited in bandwidth, so we are not using yet the 5G down there. I hope the next provider will bring down something better.
But, on a day like today, there could have been like 30, 40, 50 people in the cabin working, then everybody needs to, like the shift leader here in the control room, in case something goes wrong, needs to be able to get hold of people.
Oh, yeah, very important thing.
Oh, yeah, we are checking. So even though Andres was there in the cabin, his dosimeter is reading 0. So.
And not because the dosimeter is 40, it's because the radiation is so low.
Yeah. There's a great question about AI use. So AI is becoming increasingly more used for us. In fact, one of the ways that it's really had a really good impact is, remember when we were talking about this data flow and how we have to be very smart in selecting, because we can't store all the data, so we have to be very smart about selecting which events to keep. there's been a lot of use of machine learning in the trigger, which is the thing that selects these interesting events and is allowing us to keep more and more of the really, really interesting stuff. Hey.
Yeah. So what is important?
Welcome back.
These machine learning things that is not exactly AI, but a precursor of the AI. It has been developed for physics. So when I started my career, you don't see, but I have a gray beard now. But when I started my career, we already used something, a very, very basic deep learning algorithm for selection, for Higgs boson selection and technicolor selection in another experiment on the Large Electron Positron Collider. So something like quite long ago. And also, if you recall that the last year, the 2024 Nobel Prize in Physics was awarded to those guys who developed this kind of thing that led us to the AI today.
Yeah.
I think we also use some AI algorithms today, but obviously the deep learning is that what we are.
Yeah, we use like the boosted decision trees and that sort of thing for analyses, especially analyses where you may create maybe you make a Higgs boson, and the Higgs boson, as I said earlier, it does not live for a very long time. In fact, it decays almost instantly. So the things that you see in the detector are the products from a Higgs boson, not the Higgs boson itself. But like the Higgs can turn into different type of things, and some of them give very, very nice signals in the detector, but others the signal is much more subtle when overlaid with all of the other stuff that comes out of these collisions. And so that is where boosted decision trees and other types of things like that really help with those analyses. Yeah.
We have one more question.
Yes. So I saw in the Q&A that somebody is asking about Obscura. So this is a technical death metal band. They're pretty great. The question is about anti-cosmic overload.
I don't know what you are talking about.
So honestly, I'm a bigger fan of early Obscura, so Cosmogenesis and stuff like that. So let's leave it at that. They've had some lineup changes recently, so.
But what you may not know is that this guy, while he is an awesome physicist, he is also an awesome rock star in his own band.
Exactly.
Shameless plug.
We had a show recently in Zurich. Recently was last Saturday. So
Zurich.
So then the name of your band?
So the name of my band is nothing like Obscura. It's called Haneke Twins, Hanke. And yeah, you can check it out if you're interested.
Sure.
It's all mostly CMS people. There's only one person in Atlas, but it's all CERN people.
CERN actually has a music festival in the summer every year, and you guys have played there a few times. Yeah, so there's usually like an afternoon where they have a bunch of bands playing and stuff. So it's kind of we don't only do physics, right? We do other physics.
No. We are ordinary humans, I guess.
Yeah, and you meet.
We try to be.
You meet a lot of people with interesting hobbies, and yeah, it's actually really cool to get to know people around here at CERN. Lots of musicians, lots of very talented people, not just in physics.
Yeah.
Okay, well, thank you so much to all the team for this incredible visit and for showing the Beamline for Schools participants a little bit about CERN and the detectors and some of the nice experiments that we have here. I hope that they liked it.
Thank you, and thank you everyone for your great questions and for joining.
Oh yeah.
For the students, I will be sending a lot of emails in the comment weeks inviting you to different online events. So just pay attention, and I hope that you like the event. And see you another time.
Yep, see you soon. Hopefully see you here at CERN. So good luck for your Beamline for Schools application.
All right. Thank you for coming today. Ciao, ciao.
Bye.
Bye. See you. Thank you.